Hello, everyone, and welcome to the Wednesday press conference at the 49th DPS. My name is Shantanu Naidu, and I'm the DPS press officer. With us is also Rick Feinberg, who's the AAS press officer. We have 4 very interesting talks today for you. First one will be given by Apostolos Christou, who will talk about the population control of Martian Trojans by the Yarkovsky and YORP effects. Next will be Simone Marchi on the origin of the organic rich material on Ceres. Next will be Carrie Anderson on Titan's high altitude south polar stratospheric ice cloud observed by Cassini. And finally, we'll have Dave Schleicher speaking on the jet morphology of the rapidly changing rotation period of Comet 41P. Before we begin, may I ask everyone to turn their cell phones off or turn them on silent. We'll have the speakers speak in order, and then we'll take question and answers after everyone's done. So I'll hand it over to Apostolos Christou.
Good afternoon. My name is Apostolos Christou. I work at the Armagh Observatory and Planetarium in the UK. And today I will talk to you about a special corner of the solar system where we believe asteroids are made by sunlight. So to start with, what are the Trojan asteroids? Well, Trojan asteroids are special, is a special group of asteroids that move in sync with planets along their orbits, and at the same time keeping at 60 degrees ahead or behind of the planet. One simple analog for this configuration between planets and Trojans is to think about airplanes flying in formation. So, where do we find these Trojans in the solar system? Well, I would say that the best endowed planet in this respect is Jupiter, where we know of over 6,000 Trojans. Now, the planet Mars also has Trojans, but a lot fewer than Jupiter. Here I show all the Trojans that we know about. There are about 10. The red object is called Eureka. It's the first Trojan we discovered about 35 years ago. Next to it, you see those amber asteroids that, together with the Eureka, they form what we call the Eureka family. You also see those 2 blue asteroids there, 1999 UJ7 and 1998 VF31. These appear to be quite far from the Eureka family. In fact, UJ7 is on the other side of Mars to Eureka, and also they're far from each other. So what piqued our curiosity here, and we wanted to investigate, is why those 2 blue asteroids don't have families like Eureka does. Right, so we believe part of the answer has to do with what we call the YORP effect. So the YORP effect is caused by solar radiation being absorbed and then re-emitted by a solid body like an asteroid. If this object is not nicely symmetric or spherical, but is instead irregular, like most asteroids are, that would cause the the body of the asteroid to spin up, okay, continuously. And eventually there comes a time where all the bits that make up the asteroid cannot stay together and they start flying off. So for lack of a better term, I'll call these bits that fly off YORPlets. Okay, so once this YORPlet is lost, it then goes on an independent orbit around the sun and becomes a new asteroid. But at the same time, its orbit it's still quite similar to the orbit of the parent. Okay, so this is a reasonable mechanism to expect to see operating in the Martian Trojans, because Trojans are the closest stable group of asteroids to the sun, and YORP is powered, if you like, by solar radiation. Now, how do we go about proving this? Well, first we go to the telescope like proper astronomers, and what we do, we measure the light from the asteroids as they rotate in space, and from those measurements we can obtain the rotation period of the asteroid. So then we take this information and we and also take information on the size of the asteroids, and we put it in a plot where we compare them with the same information for other asteroids. So what we see, I would like to draw your attention to the red point at the bottom. So UJ7, this asteroid plots quite near to the green points. These are the tumbling asteroids. So these asteroids do not rotate simply around a fixed axis, but this very axis changes very rapidly in time. Now, we cannot confirm at the moment of the observations that we have that this asteroid is actually tumbling, but if it is, that could explain why it doesn't have a family, because theory tells us that YORP does not work very well for tumbling asteroids. So this asteroid, if it's tumbling, it cannot be spun up to the point where it starts creating YORPlets. Okay, so let's accept that this explanation works for UJ7. What about VF31? It's most likely not a tumbler, so why it cannot produce a family that we can see? Well, we think that the answer is a slightly different effect. This is called the Yarkovsky effect. It's also driven by solar radiation, but instead of changing the asteroid's spin, it changes the orbit around the sun. So to find out how the orbits of those YORPlets would gradually change over a long time scale, what I did is I simulated in the computer little, if you like, YORPlets, which I started from the orbits of Eureka and VF31, and then I propagate them forward in time with this Yarkovsky effect. So you see that in this plot at the bottom left. So what I find is, first of all, that eventually YORPlets from both asteroids will begin to escape. They begin to be lost from the Trojan clouds. But more importantly, YORPlets from VF31 begin to escape a lot sooner than YORPlets from Eureka. And this is actually the answer, because if we see about 10 objects from Eureka, we should only expect to see 1/10 of that for VF31, or about 1. So the fact that we see none is not really surprising. So to summarize, radiation forces, namely Yarkovsky and YORP, can create, but also can evict asteroids from the Martian Trojan clouds. The differences that we see across the 3 asteroids have to do with different balance between these 2 processes of production and loss. So the answer to why Eureka has the only family of Martian Trojans is that it is the only one of the 3 asteroids for which the rate at which new asteroids are being produced is much higher than the rate that they are being lost. So with that, I will stop here. I'll offer a note of thanks to my collaborators, and I will pass on the baton to Simone Marchi. Okay.
Good afternoon, everybody. In this talk, we are going to look deeper into the detection and the origin of the organic material on Sirius. Sirius is a dwarf planet. It is in the main belt, so between Mars and Jupiter, and it is the largest object in that region. What you see in this chart is a bird's eye view of the regions where organics were detected. This is the Ernotate crater. It is about 50 kilometers across, and it is found in the northern hemisphere of Sirius. The color coding superposed will give you the distribution of organics. Those spots that you see in red are the organic rich terrains. Before we delve deeply into the organic story, let me just give you one slide recap of what we have learned thanks to the Dawn spacecraft about the composition of Ceres. It turns out that Ceres, it is really a chemical factory. This is a list of molecules that have been detected at the surface thanks to the spectrometer, and as you see, it's pretty rich and amazing if you compare with other asteroids or other smaller objects, for instance. So we do have clays. There is also a very peculiar type of clays that is ammoniated, that contain ammonia, NH4 in this diagram. We do have also carbonates that are rather rare in the solar system, except for on Earth, of course, and so on and so forth. So it's really an interesting object. And at the end of this list, I also have what I've indicated in yellow. These are aliphatic organics. This has been detected more recently. And these are complex molecules that contains CH2 and CH3 groups. And so, an example of this kind of material is what we call kerite. This is found on Earth commonly, and it's also found on meteorites. So here we're going to talk a little bit more about the origin of these aliphatics on Ceres. I would like also to give you a little bit of better view of where this material is located. So what you see here is a portion of the northern hemisphere where Ernotate crater is located. In the blow-up portion, you see the crater. and then there is also a blow-up that comes from the framing camera, gives you a higher resolution. The highest resolution that we have here is of the order of 25 meters per pixel, so it's pretty good resolution to really find the details. The color codings that indicated from green to red gives you the concentration of organic as inferred from the spectrometer. And so as you see, this seems to be broadly distributed around this air-noted crater. So why do we care about organics? Well, there are a number of interesting things associated with organics, and well, the first one would be that organics and also volatiles, that both are found on Ceres, are clearly key ingredients for prebiotic chemistry. So that's certainly an interesting twist potentially to this detection. And also we would like to understand how the organics and volatiles have been delivered through the inner solar system, including the terrestrial planets. And the question that we'll try to address today is simply related to the origin of these organics. When it comes to the talking about the origins, we can define at least two broad scenarios, just broadly speaking. Well, in the first scenario, you have an exogenous origin for the organics that would imply that the organics have been delivered onto Ceres, and for instance, thanks to impact with other objects such as asteroids or comet, and particularly Comet 41P. It's a famous comet. It was a target of the Rosetta mission. We know there's plenty of organics on those kind of objects, and so those could deliver this material, as indicated in the cartoon. The other opposite, if you will, scenario is that this material is indeed endogenous. It would imply that it will form within Ceres, and potentially that has been excavated and brought to the surface by subsequent cratering, like, for instance, the air-noted crater that we saw. Also, we should remember from previous slides that the region where we do find organics is really heavily craters. There's lots and lots of craters. It would imply lots and lots of excavation. So either way, cratering and impacts are associated with our detection of organics. So we really need to understand what the role of the impact is. And the reason I'm insisting on the impact component to this story is explained in this chart. These molecules are extremely fragile. So what happens if you hit them up, you basically destroy the carbon-carbon bonds, and these groups like the CH2 and CH3 that are causing the absorption band, that is the detection of the organics, will be lost, and therefore there will be no detection. We wouldn't see this material. So clearly eating is a key element. Now, when you have a collision, you obviously have lots of energy, and that energy result in eating of the material. So bottom line, if collisions somehow are involved with the organics, then we need to figure out a way whether or not organics could survive the eating that results from those collisions. So this is what we're going to look more closely. And here is what I call marble plots, because that's the way they look. What you are looking at now is different impactors, and so we took a sophisticated code that actually tracked the collisions and the evolution of the temperature, the pressure of the material. And what you see here is different impactors. This is not to scale, but the details of the collision are given. So we have different velocity, different impact angles, and also different impactor sizes. And then we apply the model to investigate the degradation of organic as a result of eating. And what you see in the color coding is actually the fraction of organics that would survive the collision. So a first important conclusion here, if you look the case where the text is indicated in blue, you see that it's a high velocity, 10 kilometers per second. So this is a typical velocity you would expect if you had a comet striking onto Ceres, a comet like 47P, for instance. Under these circumstances, as you see, impactor is totally destroyed. There is no way organics could survive the collision because of the high speed. If you then consider lower impact velocities, like you would necessarily get if you had an asteroid coming from the same region colliding onto Ceres, the velocity are lower, as indicated in the other cases I have in the chart. But even then, for the most part, organics are destroyed. There is only one case in this slide, and where you have this yellowish color. That would imply that a fraction of the organics under that kind of collision could survive. What's special about that collision was simply that if you pay attention to the impact angle, it's only 30 degrees. That would imply it's a very, very shallow impact angle. So under that kind of collisions, the temperature are not so high and organics can survive. However, once you deliver this material onto the surface, you have to consider that this material is going to be diluted because it's going to be entrained and mixed into target material. And so if all the organics are in the impactor, you basically dilute them to the point that even if they could potentially survive, it's going to be extremely hard that you can actually detect them, simply because you are diluting by a factor of 10, if not more. So the conclusion here is that it appears in a way or another to be extremely unlikely that organics could be delivered by impactor either with an asteroid or with a comet. And this leads to the other options. So the other options is where indeed we have organics that were formed within Ceres. And maybe we have exposition of this material, excavation of this material through subsequent cratering. So what you see here is again another simulation of the same kind I've shown you before, where now the emphasis is to look at what happened into the target instead of what happened into the impactor. So the simulation shown in here, it's an air-notate scale of collision. So this would result in a crater of about 50 kilometers. So it's a much larger collision than what I've shown you before. Also, the chart doesn't necessarily give you the final crater. It actually takes all the particles in the simulation, put them back at the starting location, so you have a nice and clear snapshot of the temperature distribution. And while you see close to the impact point, there is certainly temperature is so high that organics will not survive. So the color coding that you see in this chart is as in the previous one. So it tells you the fraction of organics that would survive. Now, you also notice there are those gray regions and with little arrows. Those are actually indicating the streamlines in an excavation process. So what that means, to put it simply, is that that material in a gray region is what is going to be excavated in the cratering process. At the end of the day, you will get a big hole in the ground in this collision. So the material is going to be excavated and eventually will fall back close to the impact point in the ejecta blanket of the crater. So as you see, the material indicated in gray is not thermally processed. So if you have an organic rich terrain in the region in the subsurface, that material can be excavated, is not eaten to the point where organics are destroyed, and so organics would survive. So in other words, organics that were present on Ceres could indeed survive multiple impacts and can be redistributed on the surface. And the conclusion then would be that when it comes to the organics that we have detected on Ceres, these are again aliphatic organics. These are characterized by the groups CH2 and CH3. These are readily destroyed if they are coming from an impactor, either an asteroid or the comet. It appears, therefore, much more likely that this material is indeed within Ceres, and it has been excavated through multiple impacts and brought at the surface. Now, this is interesting, and of course, while we think we have a good understanding of the origin question, these of course lead to further questions for future work, and I would like to mention some interesting possible new direction. Well, the first one, if indeed we accept the idea that these organics were formed within Ceres, then of course we need to understand what kind of chemistry would produce that material, which is rather intriguing, coupled with the already rich chemistry we have already seen in the previous charts. Also, it is yet not clear why this organic seems to be localized at one point on the surface. And so the question is, are these really a localized pocket of organics, or maybe they're more widespread for whatever other reasons we are not able to see them? So these also questions need to be addressed. And finally, this will have implication, of course, in the way we understand these organics are distributed into the inner solar system. Thank you. And now I'll pass Next speaker.
Okay, good afternoon. Thank you all for coming. This is loading. So, okay, before I dive in, I wanted to tell you a little bit about myself. I'm with the Cassini Ceres team. I'm a co-investigator. And Ceres is the composite infrared spectrometer. I should say it was on board Cassini before the big plunge that happened last month. But what Ceres does is it measures the thermal infrared radiation from different objects. That's the heat radiation. So imagine yourself sitting in front of a fire and your eyes are closed and you don't see it, but you feel it. And that could give you a sense of what Ceres is recording from Saturn's atmosphere, the different icy moons, Titan, the atmosphere, the surface, all that. Another way to look at it is if you have night vision goggles on. That's what we see. So we don't need reflected solar radiation from the sun to detect anything. We have the night vision goggles on because we can see in the dark. And that's one of the beauties of this instrument, a fantastic instrument. And so what I study is Titan's particulates in the stratosphere. Now the stratosphere is the second highest layer in an atmosphere. You have your troposphere first. We're all in the troposphere right now. And then you go up to the stratosphere. Now Earth's stratosphere, when you talk about cloud formation, is quite dry. And that's because the source of water is the surface of the Earth. And you do see some clouds in Earth's stratosphere. These are the nacreous clouds that you see, the ones that have the heterogeneous surface chemistry going on to making these chlorine compounds that ultimately destroy ozone. But on Titan, the picture is very different. It has a ton of different organic materials that eventually condense out, and they form numerous layers throughout Titan's stratosphere. Because all this organic vapors, they're formed very high up, around 1,000 kilometers or so, even higher in Titan's very upper atmosphere. And so by the time it gets down to the stratosphere, Ceres can pick up on the vapor, but Ceres also sees what's condensing, the condensables. And that's what I look at. And so there's a specific type of observation that I'm actually depicting here. It's called a Ceres far-infrared limb scan. And the circle there represents the far-infrared field of view. It's circular, and what we did is we would start in Titan's lower mesosphere, and Cassini would slowly scan down Titan's limb. And these fields of views overlap by about 99%, and that's how I'm able to, after the scan is done and I analyze the data with the ray transfer model, where I'm able to essentially deconvolve this data and retrieve 40 to 50 kilometer thick ice clouds in the stratosphere. And so you have the scan here, and the curve, the white curve I'm showing you, this is a representative tangent height intensity profile from such a scan at one wave number. I'm showing you 200 inverse centimeters, it's about 50 microns. And so what happened is, so this was during northern winter, T4, so it's 2005. Cassini had only been in the Saturn system not that long, and this is during northern winter 85 north. I also wanted to say that Cassini arrived, Saturn orbit insertion was 2 years after northern winter started, but because we were there 13 years, we finally saw it kind of the onset of southern winter, and that's when I started to see a lot of exciting things going on in the South Polar region as it was heading into winter. And so if you look at, so this is during 2005. The point is that line curve rides on zero intensity until, oh, I guess I can use this, there we go, until you get down to about 160 kilometers above the surface, and then it takes off. And the increased intensity is due to the density is increasing, the aerosol are starting to kick in, and also there's a ton of different stratospheric clouds down below here that you can't see in this example here. You have to model them to retrieve them. But now if we fast forward 10 years to the T112 flyby, that was July 2015, and at 75 south, and you see there's a difference in intensity that popped out here. This is what I named the HASP cloud, Titan's high altitude south polar stratospheric ice cloud. Now it peaks around, this is a convolved view of the data, but let's say 200 kilometers you're seeing it. It's an intense emission, and so that means we have a quite abundant cloud forming here. And I had never, in the 11 years I've been with the mission, I had never seen anything like this. So this was a super exciting time, because with the naked eye, I went, oh my goodness, modeling is going to be so much fun now to figure out what we're looking at. And so, I also wanted to comment that This is the ISS VIM South Polar Cloud that you guys have probably heard a lot about. That's kind of hanging around, what was hanging around about 300 kilometers above the surface. You can kind of see it right here. Now, I'm not talking about that cloud. These are two distinct clouds. They're different chemically. Their formation altitudes are very different as well. Okay, so if we zoom in here on just another tangent high intensity profile of the data, I won't show too much data. Now I wanted to point out, this is the HASP cloud. That's the vertical signature of it. And if I do a radiative transfer model retrieval to retrieve the vertical properties of all the particulates, this is what you get. So I model usually every 5 wave numbers, spacing starting at 10 inverse centimeters, that's 1,000 microns, to about 600 inverse centimeters. And I'm able to pull out the spectral dependences. This is for a given altitude, but I can get the spectral dependence. So that's what the HASP cloud looks like. Now this is very important because the spectral dependence directly ties into the chemical composition. And that's what we really want to understand about this cloud. What does it chemically consist of? So what I do first, before I go into my laboratory and I make the ice analogs, what I first do is I look at a bunch of different saturation vapor pressure curves, or condensation curves if you want. And where these, so I have benzene, HCN, all the way to ethane at the very bottom. And the reason these are important to give you a kind of a first approximation, a good guess, an estimate of where things are condensing out for the pure compounds. And if you can see, I've superimposed where the HASP cloud resides in altitude up here. So there's 3 contenders that I'm going to start looking at in the lab: benzene, HCN, that's hydrogen cyanide, and HC3N, that's cyanoacetylene. Now, I want to say that what we get with the ice, the end result of the ice, will not represent where these are condensing out, and that's because you're in an altitude range now where you have numerous vapors that can co-condense or co-deposition. So you're forming a co-condensed ice, a mixture, as opposed to a single isolated pure ice. But this is where we need to start. The lab work is quite time intensive. I have a postdoc in there full time, but it would take me a long time to look at all these. So we start with those 3. Oh, this is just a quick view of, there's my postdoc Delphine right there, and I just want to show you, this is my ice chamber, and my spectrometer ranges from 200 microns to 0.85 microns. So I span the far, the mid, and into the near infrared to look at when I dose the different gases, and then I look at the ice analogs and what's forms, and I see if the optical properties reflect what we observe. So you're doing a comparison. But the lab work is critical. Without the lab work, we really can't identify these ices. Okay, so here's what the spectral dependence, again, of the HASP cloud you guys saw earlier. So now I want to show you, when I go to my lab and I make an ice analog with pure HCN, and I dose it at 110 Kelvin, that's more comparable to these temperature ranges where we observe the cloud. This is what it looks like. HCN has a very strong libration feature right here. It's dominant. It's hard to get rid of it. Now, if I look at what pure cyanoacetylene looks like, here you have a lattice mode. Here's the new 7-band. The point is, if you were to sum these 2 together, you would not reproduce what we observe. But now I co-condense them. So I condense them simultaneously, the gases simultaneously, to form an ice. And here you can see in blue what such a co-condensed ice looks like. It doesn't match the HASP cloud. This actually is closer to what I discovered 10 years ago during northern winter. It was a co-condensed HCN cyanoacetylene ice, but the HC3N dominated the mixture. But also the point is, it doesn't look like the pure ices, and that's what's really important. Co-condensation tells you a very different story. So now let's look at pure cyanoacetylene again, and benzene. Now benzene's very interesting. In the far infrared here in this region, it doesn't have a very distinct emission feature. Rather, this curve, this line you kind of see here, this curve, is really more representative. Think of it like a quasi-continuum source. But when I co-condense them, benzene pretty much just damps out the cyanoacetylene signature. You can still see the lattice mode a little and the new 7-band, but we don't want to go in this direction for lab work. So now let's look at HCN and benzene. So here is pure HCN again, and then you know what benzene looks like. But now we're going to start co-condensing them in different mixing ratios. First, we tried 50-50%, and this is what you get in the blue curve. Now look, you can still see that strong libration mode of HCN. Now, so that means I do not want to increase HCN. I want to increase benzene to see what happens in that co-condensed mixture. So next, we up the benzene. We look at 61% benzene. It's getting closer to the feature we observe, but you can still see that libration mode. Okay, let's keep going. Now we're going to go to 79% benzene, 21% HCN, and we do a really nice job of reproducing what we observe. So I'll go, oh, okay, aha moment, right? You have a 4-to-1 mixing ratio of benzene to HCN, and that's kind of exciting because this is the first time anyone's ever seen anything like this anywhere in the solar system. But Titan is it's the best place to be. Anyway, sorry guys. So, but now to show kind of corroboration that what I'm really looking at is true. You know, maybe that spectral shape you saw derived from those far-infrared limb scans, maybe there's something going on with those. So let's look at some other data set from the same flyby. This is what our Ceres' highest spectral resolution data look like, and this is at 225 kilometer. I think of it as tangent height, but like an altitude. So down, it's very noisy because we only have about 12 spectra average in each of these. But down here in green is that same spectrum from 2005 at 85 north during northern winter, and you can see you don't see the haystack here. But now 10 years later, not the haystack, excuse me, the HASP cloud. Haystack's another thing I do. Here's the HASP cloud, clear as day. So if I take the spectral dependence I derived from the lab work, you can see I nicely match that, but you're probably saying, wait, it's not really not perfect. And that's because these excess signatures you're seeing here are due to another type of ice cloud in Titan's lower stratosphere, something I've named the haystack. I'm not going to talk about that today, but it's about 100 kilometers deeper in the atmosphere, in the lower stratosphere. And it's unknown, and it's something I'm trying to identify as well in my lab. So the reason you're picking up on the haystack is because the Ceres far-infrared field of view is quite large when you're just doing one limb integration, and you're about 50,000 kilometers off the limb of Titan here. And so you're kind of convoluting, you're polluting the different altitude regions from things that are deeper down. But those far-infrared limb scans that I derived the vertical dependence of these ice clouds, those are done at about 30,000 kilometers, much closer, and also we overlap those fields of view. And so we can really trust what we get from that. Now we also have mid-infrared data. So when we have a far-infrared targeted observation, like I was just showing you the data from, the mid-infrared also records. And so I wanted to look to see, is there any evidence of this 80% benzene, 20% HCN co-condensed mixture? And what caught my eye is right here. This increase here in the continuum. That's broad, and that's a classic ice signal, contributes to the continuum. So if we zoom in on that, and I run a really quick forward model with all the opacity sources, you can see in the orange here that you're not reproducing that. Okay, that's good. That's reinforcing this is indeed an ice. So now if we look at just look at the effect on the continuum, this is what pure benzene would look like. It doesn't do it. Now if you look at that co-condensed mixture, look at that. So now we're building up internal consistency that we have indeed this 80% benzene, 20% HCN co-condensed ice, which has never been seen before. So my takeaway message to you guys is this. This is the first. We've never seen it. It's very exciting. And when you co-condense, you're forming a new type of noxious ice cloud. In this case, it's a benzene hydrogen cyanide hybrid. And we're seeing this in the very early southern winter polar region in the stratosphere before we headed into winter. And of course now we can't track it, unfortunately. But this is still very exciting because we're seeing the onset of things that are going on. Now this cloud, this HASP cloud, is chemically very different, as I alluded to earlier, than what I found during northern winter. And the chemical differences are really attributed to seasonal changes. One more reason why we really need to be, especially in the outer solar system, we need to be observing for a long time to catch seasonal changes. And so the reason that you see a chemical difference in the HASP cloud than this northern winter cloud is really because Titan's meridional circulation has reversed. You have subsidence bringing down very new, fresh, organic material over the south polar region. And the temperatures are also quite different. And that's why I saw that cloud move up 50 to 100 kilometers than I typically have ever observed. Thank you. Whoops. I think I just reset it. I just reset, right? Oh, there we go. Okay, there you go. Go for it.
Thank you, Carrie. So early this year, Comet Tuttle-Giacobini-Kresak came by, one of several comets that was quite bright. In particular, this comet, I'll call it TGK for short, was close to the Earth for a significant period of time, several months, and that allowed us to obtain a lot of observations from different viewing geometries. When a comet comes this close and is bright enough, we try to detect gas and dust jets within the coma of the comet, and we were quite successful in this regard. We were using 3 different telescopes on a total of 45 nights during the interval, and we saw either 1 or 2 gas jets on every night of observation. I need to back up just a brief moment as a reminder. All the material that we see in the coma or tail of a comet comes from the nucleus, and the nucleus can be quite small. In the case of TGK, it's estimated to be about 1.4 kilometers in diameter. Source regions on the surface where there is exposed ice can heat up due to sunlight as the comet approaches the sun. The heat vaporizes the ice. The gas then flows out away from the comet, and these jets of material can extend hundreds or tens of thousands of kilometers. They also will often be curved in shape because the nucleus itself is rotating while all of this is happening. We're studying CN jets frankly because CN is the easiest one to detect the details of the jet itself, but they are considered tracers of the volatiles that are really dominating the outgassing, either water, CO, or CO2. So here's an example image, and as you can see on the left, in a typical comet image, it looks really bland because it's simply brighter in the middle and fades out as you go away from the nucleus. So the first thing we do is to enhance the image by simply removing that median radial profile, and that leaves you what you see in the center image where there are 2 jets visible. We further enhance it by just color coding so that the brightest parts of the jet are in red, the faintest regions are in blue, and this allows us to get some more details out of the observations. So on March 19th, which was one of the very first nights that we were making a detailed set of measurements, most of our data were obtained in late March and late April, but we also have data over more than a 4-month interval. We see 2 jets. These 2 images are about 6 hours apart. The fainter jet that you see in the left becomes the jet rotating around about 90 degrees and is the only one visible 6 hours later, while the brighter jet that you saw in the first image basically disappears completely because its source region has moved into the night. So we have hundreds of images, and to determine the rotation period of the comet, we find images that look alike, having the same morphology, and determine the difference in time, and therefore, by doing this over and over again, we can determine rotation periods. In this case, these 2 images were taken 75 hours apart, 3 days apart, and the rotation period for the underlying nucleus is 25 hours. Now we know it's 25 and not 75 or 12 and a half or 8 1/3 because we have a lot of other image pairs that rule out all of the other options. So the determination of the period is very secure. We've done that on all the way through the 6-week interval, and this gets us the following plot where I'm showing the period of rotation on the left axis and time on the bottom axis. As one can see, at the beginning of our intense observing, we had a period of almost exactly 24 hours. You looked from one night to the next, and things looked at the very same at the same time of night, and you look later, they both had turned by the same amount. Very surprising to us was only 10 days later, the period had increased to 27 hours. And this was just an enormous change compared to what we've seen in other comets. We were further astonished when 2 weeks later, in mid-April, the period had increased to 36 hours, and by the end of April had actually passed 48 hours. So over the 6-week interval, the period increased by over a factor of 2, and that is more than 10 times greater change than we've ever seen in any other comet. If you we fit a simple curve to our observations, and if you extrapolate backwards in time to early March, we get an answer very similar to what Farnham et al. Obtained of 19.9 hours. And if you extrapolate out into mid-May, you see that the curve comes close to these 2 points. The problem here is that these gray points are gray because we are uncertain of the period, because it depends on which jet is which in the various images. We're not taking nearly as many images, so we cannot easily follow the rotation, and you have a pattern match, but did you get the wrong jets matching? So there's an alternative scenario, which are these 2 points down between 48 and 50 hours, and we cannot rule those out at this time. Show just a little movie of images that have been extracted during the second half of April, stitched together into a full rotation sequence. Earth is to scale. Remind you, these jets really are extensive in size. And the sun at this time is up in the upper left to the northeast, and you can see that each jet is at its brightest as it is basically passing the sun, and that's because its source region is getting the most intense sunlight near noon, local noon. And in both cases, the jets also then essentially turn off at night as sunlight goes away, and therefore you stop your heating of the source. So what is causing this? The easiest answer, and probably the most likely, is simply the jets themselves. They act as rockets, action and reaction. The jet basically is applying a torque back on the nucleus itself and attempting to push it the other direction. Key point in the case of TGK is just that this is a much larger amount than we have ever seen before, more than a factor of 10. And to get such an extreme change in rotation period requires a really favorable set of circumstances. In particular, you probably need the jets to be near an end of the nucleus so you can apply maximum torque. It might imply that you have a relatively elongated nucleus, because then that also makes it easier to do the torquing. The density of the nucleus might be on the low side, and you probably have a small nucleus, and that's one part of this we actually do know. It is a very small nucleus, so it's easier to do any type of torquing. And I produced this little model, and I'll just show it where you've got a nucleus elongated, 2 jets attached to this, and as this is going around, you're seeing the spirals, but at the same time, these jets are attempting to turn it this direction, and therefore the net result is, while it's continuing to go around clockwise from our point of view, it's starting to slow down because the jets are both opposing that direction. So a particularly interesting and intriguing characteristic is that if it was going from 20 hours up to 48, 50 hours during this orbit as it passed the sun, passed close to the sun, what was it doing in previous orbits? And if you assume about the same rate of change at each of the previous orbits, you get back to the early 2000s, and at that time, you would expect the rotation period to be perhaps as fast as 2 or 3 hours. Well, that gets you into the realm of where the comet nucleus can be unstable because it just can't hold itself together if you're spinning too fast. And so it's a very intriguing possibility that that threshold was reached in the early 2000s, and I don't think it's a coincidence that in 2001 there was a major outburst of the comet. It brightened by nearly a factor of 1,000, and that outburst may in fact be an indicator that that's when the comet was disrupting in at least some characteristics. Whether a piece broke off, whether there were landslides happening on the surface, we can only speculate at this point. But this is the first time there's been a potential connection between what we see in terms of rotation and a large outburst in the comet. And finally, going the other direction, in the next orbit or two, we'd expect the comet to completely stop and start spinning up in the other direction, but we might also get tumbling because we have more than one jet involved. Finally, I'll note that we've begun doing modeling of all of this, and the model is shown on the right, and I've color-coded the 2 jets so it's easier to distinguish them. And at the moment, our model works quite well for April, but not as well in March, and we need to do a lot more work in testing the various parameters associated with the model. And so I will leave it there.
Thanks to all the speakers. Very interesting talks. We'll take questions now. Wait for the microphone to ask the question, and please state your name and affiliation. Kelly?
Yeah, I'll break the ice. Kelly, BD Sky and Telescope. This is for Carrie. If I read your plots right, it looked like the opacity of this cloud was about 0.1. So it's not a really dense cloud. And I guess the nature of my question is, what's the difference between this cloud and haze layers that are in the Titan's atmosphere?
Okay, that's a great question. Now, I didn't show the actual optical thickness, but you're right. In the stratosphere is quite optically thin in general. And so if you can imagine, these clouds probably look more of a wispy kind of cloud, but you have a lot, but it's a very extended altitude range, but confined in altitude, and that's the big difference, well, one of the differences between the stratospheric clouds and the aerosol. The aerosol is everywhere, it's ubiquitous, and the aerosol does form from photochemistry induced very high up from methane and N2 initially, and then you incorporate all kinds of nitriles and hydrocarbons that go into the formation of the aerosol. You eventually polymerize it, and it'll end up landing on the surface as a refractory particulate. The ices now, they also have a similar formation method from the trace vapors get formed in the very upper atmosphere, just like the aerosol starts to form. But these ices, they follow more condensation curves. So depending on the saturation vapor pressures and the abundances and the temperatures, once you get down to the stratosphere, then you start to condense out these ices and make them. And then they will precipitate as well onto the surface, and most of them will land on the surface in a solid form. And so this is a great way to bring down the organic material from the atmosphere onto the surface. And I also wanted to say that the condensation is heterogeneous nucleation, so it needs a seed nucleus to condense out on, and the aerosol is the seed nucleus for that. I also wanted to comment on that the stratosphere will be layered in clouds, and the ultimate sink mechanism for most of the organic vapors is condensation in the stratosphere, where the aerosol it'll either get condensed on, but the aerosol just continues down to the surface.
Emily?
Emily Lakdawala, the Planetary Society, also for Carrie. In your answer to Kelly, you said that this material is condensing as ice and eventually winds up on the surface. So to clarify, are you saying that it snows this material on
It
Titan?
precipitates, yes.
And are there any other materials that would also snow? Would they do that under different temperature, like at different times of the year? It would snow benzene one time of year and snow like.
Well, actually, the stratosphere, the lower stratosphere and the middle stratosphere, these form. You can get clouds. You tend to see them during northern winter at the northern polar region, or the winter polar regions, because you have subsidence, and the rate of subsidence is bringing down a lot more material, these organics, these vapors, to condense out. And so we usually see an increase in abundance because of that. But if you look at other latitudes, condensation is still occurring in the stratosphere at the mid and the lower latitudes. You may not see it as easily because the abundance is just too low. We can't pick up on it. But I have seen this during northern winter. I saw, as a function of pretty much all the latitudes from both poles, this co-condensed cyanoacetylene and HCN. The altitude location varied. That was the difference, because it was warmer at the lower and middle latitudes than at the winter polar latitude. So.
Yep.
Rich Talcott, Astronomy Magazine, for David. Obviously, Comet 41P has been around since a long time before 2001. Do you have any indications or ideas as to how it settled down into near breakup speed in 2001 from what it was before?
It's really unknown. I will note that the comet itself was discovered 3 different times independently over a 100-year interval. And that implies that over the intermediate times, you probably did not have major outbursts. But in 1973, there were 2 outbursts just as large as the one in 2001, and they were about 2 months apart. And so there is this real question of, was it also at breakup speed back then, and did it relax, slow down, spin back up, and hit the barrier once more in 2001 or not? And besides, in the future, if it starts spinning up the other direction, presumably in another 20 or 30 years, it would come up to that point yet one more time.
We have time for 2 more questions. If you have questions for Dallas or Simone. Yeah.
Can I ask a question?
First Joshua, I think.
Josh Local, freelance. So about Ceres, what if this belongs, in the ground underneath this crater? What would the global distribution of this stuff look like? How much could there be? Why is it there?
Yeah, there's a number of interesting implication that comes to your question. As already noticed in the talk, we do find this localized material, and we don't really necessarily understand why it's exactly there. There is nothing really peculiar about these regions. As we know, there are many other places on Sirius that are remarkable. So we have mountains, or we have these famous bright spots. There is nothing like that next to this region. So it's a little bit unclear why there should be a concentration in just one spot. I would perhaps tend to prefer an alternative option, that is, these organics are indeed widespread, and there may be processes that would hide that material, and so we are not able to see them, but they may be there. There are additional indications, perhaps, to support this claim. Overall, the albedo, it's very, very low. It's extremely dark, and so one thing could be that there's organic material in a form that we are not able to pick up somehow with the spectrometer, and this organic material could give you the very low albedo that we see elsewhere. So I do believe that organics are more widespread than we can actually say.
Great. Kelly, I think, raised his hand first.
Sorry. So this is for Tolos. I'm a little unclear how you keep track of a family within the Trojan cloud. How do you trace their orbits? Because they're librating, don't you tend to lose track? And if you don't lose track, can you work it backward and estimate how long ago they broke up?
Okay, so the first part of your question, what we do is we don't actually look at at the actual position of the asteroids. We look at how how far they are from the libration center. And that gives you, if you like, one coordinate. So it basically, you compare all these coordinates for the asteroids, and you get this clustering, and then you do the same for the other orbital elements, the eccentricity and the inclination, and you also get a clustering for the same asteroids. And that's a very strong signal that there is a significant concentration. Now, on the issue of tracing it back, okay, yes, that's in principle possible. In fact, I've tried it. The problem there is that this family appears to be quite old. It's at least several 100 million years old, possibly up to a giga-year. And it's not really, it's, if you like, it's so long an interval on time so that any information on the, any orbital information on the origin has been diluted by other effects. For example, the perturbation by the planet. So maybe if it was 10 million years or a few tens of millions of years old, it would have been able to do exactly what you suggested, but not in this case. The family is just too old.
All right, with that, we'll end this press conference. If you have any other questions, you can approach the speakers after the conference. We'll have another press conference tomorrow at the same time, 12:15 p.m., and we'll have 4 more interesting talks. Hope to see you then. Thank you.